For these, you find the eigenvalues, eigenvectors eigenvalues are a lot easier. What's a triangular matrix and what's a diagonal matrix? Your zeros on the leading diagonal, either below or above are zero, aren't they? Yeah? All the entries are either below the leading diagonal are zero or above the leading diagonal zero. What about diagonal matrix? What's that?
Is that just one way it's like the equivalent of a line or something? Like
yes, all the non-zero entries are on the leading diagonal. Yeah. Okay. So here are some examples. There's 3 examples there. Okay. What's the first one? What about this one here? What kind of matrix is that? That's a diagonal matrix, isn't it? Yeah. On both sides of the diagonal, leading diagonal. This is your leading diagonal. Okay. Remember that. Both sides is equal to 0. And what about B? Yes, triangular matrix, but which type? Upper triangular matrix. Yes, upper triangular, because the non-zero entries are above the leading diagonal. And what about C? A lower triangular matrix, isn't it? It's a lower triangular matrix. Okay. Now, guess what the eigenvalues? This is what I thought. This is what I wrongly thought that Patrick and Rachel were telling me, and they weren't. They were just saying use the result from before. Guess what the eigenvalues? Guess what the eigenvalues of this matrix are? Yeah, it is 1, 2, 5, 4. Guess what the eigenvalues of this matrix are? Yeah, 8, -8, 5, and 4. And I bet you can't predict the eigenvalues of the matrix C. Too hard.
Is it -9?
Yeah.
3, and the -1 and the
10. Exactly, that's what it is. Okay.
Yeah.
Now, of course, just because it works for this doesn't mean it's generally true. We've got to actually prove this. We've actually got to prove that this is always the case. If you've got a triangular matrix, that's why I said those triangular diagonal matrices are good. Okay. Let's prove it. Let's prove that if you've got an n by n diagonal or triangular matrix, then the eigenvalues of A are entries along the leading diagonal. How do we prove this result? How do we prove this result? It's proposition 7.6. How do we prove that? How do we prove that? What do you call it? That the eigenvalues are on the leading diagonal. How would you prove this? Well, normally in mathematics we have this something called without loss of generality. It means consider one particular case. You don't want to do it for every, prove it for every single case for a lower triangular matrix, an upper triangular matrix, and a diagonal matrix. All you're doing is carbon copying the same proof. Okay, so in mathematics we say without loss of generality, let A be an upper triangular matrix. Yeah. Okay. So WLOG, let A be an upper triangular matrix. All right, so let A equal, let's say, A11, A12, A1n, okay? 0, isn't it? Yeah, it's upper. It's going to be 0 there, isn't it? Yeah. It's going to have zeros all the way. Zeros, A22, 0, 0, A2n, I'm going to have ANN. Now I want to show, what do I want to show? Required to prove what? What do I want to show?
You want to show that is
No, it's a triangular matrix already. You're given a triangular matrix. What do you want to show? Sorry? Yeah, that's how we do it. But what do I want to? What's my last line going to be? So A11 is what?
A11 to AN.
Nearly, not quite. Yeah, A11 is lambda 1, A22 is lambda 2, A3 is lambda 3. Yeah, we want to prove, don't we? We want to show required to prove this. Our last line required to prove is lambda 1 is A11, lambda 2 is A22, and lambda n is ANN. Yeah? What's what we want to prove? Can we prove that? We want to prove that. How do you prove this then? That's our goal, isn't it? Our destination is to prove this. How do we prove this? How do you find the, go on then, Patrick. Sorry, it's a feek. How do we find the lambdas? Yeah, or determinate, yeah? Determinate, yeah? So det A minus lambda I What do we get in this case? Determinant of what? What do we get? Yeah, it's all it is. The same matrix, isn't it? With what's changed for this matrix? The same matrix, but what?
Minus lambda.
On the leading diagonal, is it? Yeah. So it's going to be A11 minus lambda, A12, all the way to A1n. Okay. 0, A22 minus lambda, A2n, 0, 0 all the way to ANN minus lambda, isn't it? Yeah, that's what that's equal to. Okay. So what's the determinant of that matrix? Come on. Yeah, go ahead,
So
Patrick.
we're going to have A11, then you're going to then it's the minus lambda,
Yeah,
then you're going to have A22 minus lambda.
exactly. Yeah, it's a product, isn't it? It's the
Yeah.
product. Is what you said. You already said the first hour, didn't you? Or just 5-10 minutes ago. I mean, the first 10 minutes ago when you said, "Oh, this is the way to do it." Yeah, you're right. Remember if you go back to proposition, I can't remember what proposition it is. I can figure it out. If you go to proposition 619, the last chapter, we showed that the determinant of a triangular matrix is the product of the entries on the leading diagonal, isn't it? Yeah.
Yeah.
Okay, that's what it's equal to. So this is equal to A11 minus lambda, A22 minus lambda, all the way to ANN minus lambda, and that's got to equal 0, isn't it? For it to be an eigenvalue, you've got to equate to 0. Remember, determinant of A minus lambda is equal to 0. So what's lambda 1 equal to? Yeah, it's A11, isn't it? That value, yeah, that value. So hence lambda 1 is A11, lambda 2 is A22, and lambda n is ANN. That's why you're quite right to say that if you've got a triangular matrix or a diagonal matrix, all you've got to do is read off the leading entries on the leading diagonal. That's all you've got to do. That'll give you eigenvalues. And with eigenvalues, you can do quite a lot. You can tell if it's we'll do proposition in a minute. We'll show that has it got an inverse or not, just by looking at the eigenvalues. Okay, so if you've got a triangular matrix or a diagonal matrix, makes life a lot easier. It's easier to deal with those matrices than not one of those. So what about, this matrix here? So you've got to determine, you get this in the exam. Before I forget, when you come back in the new year, you have no lectures, you just have an exam. You shouldn't, is the examination timetable published or not? It is. Sorry? Which was linear algebra?
I don't know. I'm not.
12th, is it?
I kind of
Okay.
haven't even seen the timetable. I got a bit confused by that.
Sorry? You might have, but not for linear algebra.
I know,
nothing.
that was why I didn't realise.
Yeah.
Because you have one
All
for
right.
statistics. That was why
Yeah.
I asked him, we have one for linear algebra.
No. What's the eigenvalue of this matrix? What sort of matrix is it? What sort of matrix is this? Come on, what matrix have we got there? Go on,
We've
Patrick.
got a triangular. mate.
Have you got a triangular matrix? So what's going to be the eigenvalues of that matrix? You've got a triangular matrix, these are all zeros, yeah? There's an upper triangular matrix, yeah?
Yeah.
So what's the eigenvalues? Yeah. Lambda 1 is 5, lambda 2 is 9, yeah? Lambda 3 is 6, and lambda 4 is minus 17, isn't it? It's the entries on the leading diagonal, that's what they are, aren't they? Okay, so much easier. So if you have, let's look at some properties of the properties of eigenvalues and eigenvectors. What is this property? What does this say? This one here. What can you say? What does this mean? Like I say, in everyday English language, what does this mean? A square matrix A is invertible if and only if lambda is equal to 0 is not an eigenvalue, of course. Thought it said is it, but it says it's not an eigenvalue. So, yep.
Does that mean that A has no inverse if lambda isn't zero? Lambda's got
Yeah,
like
if
a
it-
non-zero value.
Yeah, yeah. If all the eigenvalues, you've got a zero value. If you find that one of the eigenvalues is equal to zero, you could definitely say it's got no inverse. So you don't. There's no point trying to find a unique solution. You will not have a unique solution to a linear system. Okay, it's a good test. So you find the eigenvalues. If you find that one of the eigenvalues is zero, or if you've got a triangular matrix, one of the entries is zero, then it's going to have no inverse. Okay, it's not going to have inverse. It's not an invertible matrix. Okay, let's have a look at this one. What does this say? These two say 7.8. What does A say? What does A say? Let's look at A, and then I'll prove A in a second, and I'll leave you to look at B. What does it say? Come on. Yep.
Is it just like saying that when A is like have an M, like when A is to the 2, lambda will be lambda to the square or something?
Yeah, it will be, yeah. So if if A has an eigenvalue, let's say A has got an eigenvalue of 2, okay, then A cubed will have an eigenvalue of what? Not 2. 8, yeah, 2 cubed, yeah? That's what it's saying. It'll be 2 to the power 3, yeah? With the same eigenvector, okay? Let's prove this. How do we know that, AM is going to have an eigenvalue, lambda M, if our eigenvalue of A is lambda? How do we prove this? Proof of A. Well, let U be an eigenvector belonging to lambda, yeah, of A, let's say. Yeah, A is any matrix, yeah? So what can you say with that? What can you say? Come on. Well, for the definition, we know AU is lambda U, don't we, yeah? What do you want to prove? What's our destination? Required to prove what? What do we actually want to prove? That's the way, some of you said you find proofs very difficult. I mean, you see the way I do them. Hopefully this video will be uploaded. Okay, see the way I do them, and then you'll get used. You say, oh yeah, this is the way. Well, I want to go about doing these proofs. Yes. Look at your destination. If you know where your destination is, then the proof is a lot easier. At least you know what you're trying to achieve.
So I guess what we should try and prove is that when A squared.
Yeah, or A to the M U is what?
U is lambda.
Yeah, lambda M U. Yeah, we want to prove that, don't we? Yeah. Okay, we want to prove that. How are we going to prove this? M is a natural number. M is a number like 1, 2, 3, 4. So it can't be a half. Can't be square root of A. So how do we prove this? What sort of proof are you going to use? Yeah, induction. Yeah, it's good. Well, that's to be. If you want to see M, a natural number, you want to look at proof by induction. Now, there's 3 steps in proof by induction. Okay, what are the 3 steps?
Well,
proof.
First you do it for M equals like 1 or 2.
Yeah, induction. Step 1. Okay. Check for M is equal to 1. Yeah, let's say M is equal to 1. Okay. Well, M is equal to 1. Is it true?
Yeah.
Yeah, of course. It's there, isn't it? That's the definition, isn't it? Yeah. That's the definition. We have AU is equal to lambda U. So that works, doesn't it? Yeah. Okay. What's step 2 in?
Well, we do K.
Yeah. Assume. Step 2. Assume the result. Assume the result is true for M is equal to K. Yeah? How do we write that down then? How do we write down this result then? Yeah, A K U is equal to lambda KU, isn't it? Yeah, let's call this star or something. Yeah. So what's step 3 then? Yeah, we've got to prove it, don't you? Yeah, it's required to prove step 3. Okay, we need to prove. We need to prove that we need to prove that a to the k plus 1 u is equal to lambda k plus 1 u. Yeah, that's what we want to prove, don't we? Yeah. Okay, so if we consider the left hand side, take the left hand side. Consider the left hand side. So a to the k plus 1 u, if we write that, what do we get? Yeah. Well, if we're a to the ku, yeah, we can definitely do that, can't we? Yeah, that's definitely true. We can do that, can't we? Yeah. Okay. Yeah, by using star, we know that's by using star AKU is equal to lambda KU, isn't it? Yeah. Okay, by star. Okay, so we get a lambda KU, don't we? Yeah. Okay. Yep. We want to prove it's k plus 1.
You can then just go and swap the a and the lambda k around.
We can swap them around because the scalar, isn't it? Yeah. Lambda is a scalar. Okay, we can write this is equal to lambda k AU, can't we? We can definitely do that, can't we? Yeah.
And you've got what AU equals.
What does AU equal?
That equals lambda.
Yeah, exactly. AU, there it is. The first. Sorry, you can't see it. AU is equal to lambda U, isn't it? Yeah. Okay, AU is equal to lambda U. The first one we checked. Okay. So substituting that in there, we get substitute that, we get lambda k lambda U, and what does that equal then?
That can equal lambda k plus 1.
Lambda k plus 1, which is U, which is what we want. Look, we want to prove that, and we've done it, haven't we? AK plus 1 U, the left hand side is equal to lambda k plus 1 U. Yeah, we've done it. End of proof. So proof by induction that if lambda is an eigenvalue of a, then a to the cube will have an eigenvalue of lambda cubed. Yeah. If a has an eigenvalue of 5, then a to the what do you call it? A squared will have an eigenvalue of 25. Yeah. Same eigenvector. The eigenvector doesn't change. That remains the same. You can check that. Okay. Okay. One of the what is this second part B? I'm not going to prove this, but you can look at my proof. What does part B say? If A is an invertible matrix, then the eigenvalue of the inverse matrix is what? If A is invertible, then what's going to be the eigenvalue of the inverse matrix? 1 over lambda, yeah? That's why. So what about if A is not invertible? So it works when A is invertible. What about if A is invertible? Then what? Then what would be the eigenvalue? We did a property just now. How do you know that matrix A is invertible? There's many checks you can do. What's one check you could use determining using eigenvalues, eigenvectors? How could you say that A is invertible or not? Something to do with eigenvalues, eigenvectors. Yep. Yeah, it can't be 0, yeah, okay. If one of the eigenvalues is 0, then it's non-invertible. So that's why you've got 1 over 0, you can't have 1 over 0, okay? That's why it's going to have A is invertible, yeah, that's what it says. A is invertible, then the, what do you call it? The eigenvalue of the A minus 1 will be 1 over lambda. So if A has an eigenvalue of, let's say, 2, what's an eigenvalue of A to the minus 1? Come on. Sorry? Yeah, half. Yeah, exactly. If A has an eigenvalue of 5, what's an eigenvalue of A to the minus 1, the inverse matrix? Sorry? Oh, 1 over 5, yeah, for fifth. Okay? So, that's what it says. So you can have a look at this. So look at what it says. Same. This is if you put it in a table. This is what you get. The power lambda m inverse lambda minus 1. Yeah. Okay. Same eigenvector. Eigenvector remains the same. Okay. Let's do this example then. If you've got this, find the eigenvalues of a. What of a to the 7? How do we find the eigenvalues of a to the 7 of that matrix?
Firstly, you should work out A, shouldn't you?
No, a. So you're given.
Yeah.
Yeah. What's the eigenvalues of a then? Oh, you mean eigenvalues of a?
Yeah.
Yeah. Oh, yeah. Sorry.
Look
Yes.
at the eigenvalues of A,
Yeah.
then
Yeah.
you can
Yes.
work out. Then
Of course. Yes. You need to
it'll
find
be
them.
easier to work out the
That's right.
eigenvalues
Yeah.
of A
Yeah.
to
The eigenvalues of a are what? Yeah. It's a triangular matrix, isn't it? Yeah. The triangular matrix.
Yeah.
The eigenvalues of a are 1, 2, and 3. Clearly, there you are.
Yeah.
The entries on the leading diagonal, aren't they? Yeah. Okay. So what are the eigenvalues? Sorry, you got a question or you going to answer
No, I was
something?
going to answer it.
Okay. What's the eigenvalues of a7 are what?
Well, they're going to be 1 to the 7.
Yep.
Then 2 to the 7.
Yep.
Then 3 to the 7.
Exactly. Simple as that, isn't it? Yeah. 1 to the 7, 2 to the 7, and 3 to the 7 are going to be the eigenvalues of a, clearly. Okay? So you don't have to, work out a to the 7. There's the eigenvalues a to the 7. Okay. Okay. Let me do one more proposition. What does this proposition say? Let A be any n by n matrix, okay, with eigenvalues lambda 1, lambda 2, all that. And then what's the first one say? What does that say? Like I say, you need to decode this into everyday English language. No point just sort of reading math notation. You know what it means. Yep, go on, Rachel, what does it say? Yeah, yes. They say the determinant of A is a product of the eigenvalues, yeah? So if you've got an eigenvalue, if you find the eigenvalue of the matrix A is 1, 2, 3, what's going to be the determinant of that matrix? Yeah, 1 times 2 times 3, it's going to be 6. Okay? It's going to be 6. If you find the eigenvalues of matrix A is 1 times 1, 2, 3, and 4, what's going to be the determinant of the matrix without working it out? Well, they only use eigenvalues. Don't work out the long way. What's it going to be? Come on. If you've got a matrix A, 4 by 4 matrix, and the eigenvalues are 1, 2, 3, and 4, I say work out the determinant of this matrix. What's going to be the determinant of that matrix? Sorry? Yeah, 24. 4 times 3 times 2. Yeah, 4 factorial. Yeah? Okay? It's going to be the product of the eigenvalues. Okay? The trace, I've talked about the trace. I'm not too worried about this. Trace is not as important as the determinant. The trace, what does the trace of a matrix mean? What do you mean by the trace of a matrix? Don't recall. Doesn't matter if you can't, because I haven't really. It's not been the central of my study. If you don't know what the determinant of a matrix is, I would worry about that. If you don't know the trace, I wouldn't be too concerned. Can anybody recall what we meant by the trace of a matrix? Yeah. Yeah, it's the addition. It's instead of multiplying. It's the addition. Okay, of any 2 by 2, 3 by 3, whatever it is. It's the entry added on the leading diagonal. Yeah, you add the entry on the leading diagonal. That's what that's equal to. Okay, so the trace is given by lambda 1, lambda 2 plus lambda. So when you add the eigenvalue, you get the trace of the matrix. The trace is not too difficult. Once you're given the matrix, the trace is not too difficult. You can use it as a check. See if you've got the correct eigenvalues. You can use it as a check. Have you got the correct eigenvalues as well? It's a very good check. I can't guarantee it'll work because you might get -1 plus 1, then you might get -2 plus 2, maybe the eigenvectors. You add them, you get 0, don't you? Both cases. So you can't use 100% as a check. Okay, so what it says really is if these are if you look at this table here, it says that. What it says is this. Is this. Matrix A, the eigenvalues are lambda 1, lambda 2, lambda n. The determinant is the product, and the trace is the addition of that matrix, yeah? Okay, now let's have a look. Find, say you're given this, says you're given that, and you're told the eigenvalues are 1, 4, and -1. So what's going to be the determinant of this matrix? What's the determinant of this matrix? -4, yeah. 1 times 4 minus 1, yeah? Okay, 1 times 4 is 4, 4 times -1 is -4, yeah? That's the determinant of the matrix. What's going to be the trace of the matrix? 4, yeah. 4 plus 1 minus 1 gives you 4, yeah? And if you add those entries, that should add to 4. 1 plus 1 plus 2 gives you 4 as well. Okay, so it works in that case. It works in general terms. Just before we finish off, I want to come back and do the Cayley-Hamilton theorem. But what you should know is if you've got distinct eigenvalues, then the eigenvectors, the corresponding eigenvectors, will be linearly independent. Okay, that's an important theorem. Not worried if you can't prove it, but if you've got different eigenvalues, then the corresponding eigenvectors will be linearly independent. You want linearly independent eigenvectors. Okay, I'll come back and do the Cayley-Hamilton theorem on Thursday.